Okay, here we go. Question 6.1 has several parts, and we're looking at part D. So the system was ax minus mxy, by minus nxy. And with this, you can, or I should say, if you want to graph the following curves, you want to graph, let's say, 0 is equal to dx dt. That's the same thing as saying 0 is equal to ax minus mxy. You can factor out the x, leaving you with a minus my. And now in order for this to be true, there's essentially two components. You could have the x value be equal to 0. So you could get x is equal to 0. Or you could have the expression in parentheses equal to 0. That would give you, for instance, a minus my is equal to 0. And hence you would get that a divided by m is equal to y. You can then take and graph these two lines from this single equation. So if we have our system here with an x and a y, or our axes here, then we would get two different values. Get x is equal to 0, which I guess is just this. And then you'd get y is a divided by m. We know that a and m are positive, so we get this. This just came from the first equation. If you do the second equation, you'll get exactly the same thing. But in that case, what you get is that y is equal to 0, giving you this. And then you'll have, let's see, x is equal to b divided by n. And now this will be your 9 regions. In each one of these regions, what you want to do is see where dx dt, dy dt are positive or negative. If I, let's say, graph this in, or color this in orange, and I color this one in, oh, let's just use white. What we get, say, let's see, maybe this region, any one will work. But in that region, we have that y is greater than a divided by m, and x is positive. So since x is positive and a over, or rather y is greater than a divided by m, what that implies in this region is that dx dt is going to be less than 0. That gives us this arrow facing this way. And then correspondingly, let's see, if y is greater than a over m and x is positive, what do we get there? So we have by minus n y over b minus nx. Here we also know that x is strictly less than b over n. Y is positive. So that means we have this arrow up like this, because then this is all positive. And now what that gives us, actually, maybe I should do this purple. And now what this gives us is an arrow facing up and to the left. So like this. And now you can do this in every one of the different regions. I'm going to erase this work. Do this in every region and all the 9 different regions, and you'll kind of get a sense of how solution curves might move around in the plane. And then that leads into E, part E of written homework 6, then essentially says, it seems like eventually one of the populations will die out. And if you have a solution curve that, let's say, looks like this, or maybe if I do a little more carefully, say it looks like this, it looks like the population will eventually, the Y population will eventually go to 0. Correspondingly, if you had a curve that looked like this, it looks like the X population eventually goes to 0 over time, and so on. But if you had something like this, for instance, it looks like neither one of the populations are going to go to 0 in this case. You might just kind of rotate around like we saw in the previous written homework, and neither one goes to 0. That might be the case, but what you would see is from the way these arrows are set up, I'm not sure what the other regions look like at the moment, but you would see from the regions whether this is true or not. Okay, that is the last part of that problem. There was another request to go over written homework 7, part 1, I believe. So let's take a look at that. And I think this will lead into our discussion today. So 7.1, just reading this over, written homework 7, question 7.1. We're given a series, a power series. We have this power series like so. And if you're thrown off by power series, it's okay. There'll be, well, there is currently a video up on it that would in theory be something to watch tomorrow, but we'll also talk about series today. So if this is seems a little foreign or foggy, we'll certainly be talking about it. And what we're given is that y of 0 is equal to a naught, or we're claimed that y of 0 is equal to a naught, y prime of 0 is equal to a1. And then you're asked to find the general form of an. So it's a little preview of series. And if, again, this doesn't make sense at the moment, that's okay. We'll talk about it. There's a video on it for tomorrow. But what this means, this series notation here, it means that you have a sum where you start at the index n is equal to 0, and then you increase it by 1 each time. So first you have n is equal to 0, which gives you a naught x to the 0. Then you have n is equal to 1, which of course gives you a sub 1 x to the first plus a sub 2 x squared, and so on. If you substitute in 0 for x, that will give you a of a naught x to the 0 is just 1, so there's no substitution there. Then you have a1 to the 0 plus a2 to the 0 squared plus etc. And that'll just leave you with a naught. From there, what you can do is you can go back to this series representation, differentiate all the terms, and then do the same type of thing where you substitute in 0 and see what value you get. The claim is that you should get just a1. Now, just to be maybe a little more clear, if you take y prime of x, you take the derivative of each one of these terms. This is a constant, so you get 0 to start. Then you have a1 times x, take the derivative, and you get a1. Then with the next one, you have a2x squared, so you get plus 2a2 x to the first power, plus, and then just to see the next one, we get 3a3x squared, and so on. Substitute in 0 here, and I think you can see that you'll be left with a1 because all these will be 0. But then you want to do that for y double prime and y triple prime, which is not very hard because these are easy to differentiate. But then see if you can find a pattern for a sub n. We know that a sub 0 is y of 0. We know that a sub 1 is y prime of 0. And a sub 2, maybe that's like 17 times y of 0. This is not true, but just as an example, maybe it's something like this. And then maybe what you can do is you can find a general formula, a sub n, and then you can write that as like, oh, the nth derivative of y, evaluate some number, divided by something or whatever. There should be some formula there. All right, so that sets up 7-1, but that again assumes you're a little bit comfortable with power series, which we'll certainly be looking at this week. All right, with that, let's go ahead and jump into it. So sequence and series, just as a reminder, this would be, again, things we have seen in Calc 2, but it's, been a minute, I think. A sequence is just an ordered list. It doesn't have to be infinite, though oftentimes we will take it to be infinite, but it's really just an ordered list, such as 1, 2, 3, 4, 5, 6, etc. Or 1, 1/2, 1/3, 1/4, and so on. And here are just a couple. But you could have a variety of things. There could be a pattern. There doesn't have to be. But these are just some. You could alternatively alternate. You could go 0, 1, 0, 1. But that's all there is to it. Just an ordered list. There's a first thing, a second thing, a third thing, and so on. And if you want to know more clearly what ordered means, there's a bijective function between the natural numbers to some set. That's the same as saying there's a first thing, there's a second thing, there's a third thing, and so on. All right. Then you can take and generate a series, which is just simply a sum of a sequence, or the sum of the terms of a sequence. Some examples of this, well, I could just put plus signs between every single one of these terms here. And I could get something like 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus etc. And all these that I'm writing now, these are all examples of series. And so on. Now, one of the most important things to ask about a series is whether it converges or diverges. Some of these series that I've written here are what's called convergent, and then others of them are what's called divergent. And it's essentially, does your series somehow mystically add up to a given finite number, or will it add up to infinity, negative infinity? Will it not add up to anything specifically? So let's take a look at what it means to be convergent. So here's the formal definition. We say a series written in compact form like this. And just to be clear, when we say this notation, what we're saying is this is some a sub 0, because this starts at n equal to 0. Actually, I'm going to jump back. I want to explain this in more detail. I kind of assume it might be obvious, but there'll be a point where we have to change indices. And actually, I think it's maybe not so obvious, or we maybe just don't have that much practice working with the indices. So let's be really careful. If you have this notation, actually, I'm going to even say let it be I, and we go up to n, capital N. No, I don't like that. Let's start. How do I want to call this? Let's say A, B. And you have the series C to the N like this. Hopefully this is not too many letters, but I need a sensible place to start it and end it. What we get is the following. We get C sub A plus C sub A plus 1 plus C sub A plus 2, and so on, up till we get to C sub B minus 1 plus C sub B, like this. So we have a starting index. Let's say that's A. Color that magenta. That's what we have here. Then we have an ending index. We'll color that cyan here. So when we write this notation, all we're saying is that it's the sum starting at C sub A, and then you increase each time by 1 up until you get to C sub B. As an example, if you had, let's say this, about 2 factorial over, or not 2 factorial, let's do n factorial over 3 to the n, and maybe that's just it. And we go from n is equal to 2 up to 5. 5 would be our ending index, and 2 would be our starting index, or maybe starting index value. So this would look like 2 factorial, 3 to the 2. Then we would have 3 factorial, 3 to the 3, plus 4 factorial, 3 to the 4, plus, and then the last one is going to be 5 factorial, 3 to the 5. And in the middle there, the indices were 4 and 3 between the starting and ending index. Okay, I want to pause now and just ask, is this making sense, what I'm going through here, or is any of the notation confusing? If anything's confusing, it's easier to ask now rather than later, because here we're kind of working with the simplest examples, and then later we're going to add, x to some power and so on. And then we're just it's going to be more to keep track of. Okay, I've only heard from a few people. So it means the rest just aren't listening, or what? Okay, so it seems like it's making sense. Thank you to those who responded in chat. Now then, let's jump to convergence. Oh, I should say one more thing. And maybe it's clear, but I really want to make sure it is, to help just make it easier for you later. If we have infinity up here, but maybe we have something like, I don't know, 6, and we have the same type of case, this infinity represents just going on infinitely far with the terms and never stopping. So we would have, say, 6 factorial, 3 to the 6, plus 7 factorial, 3 to the 7, and so on. And then we would just keep going. So that's what that infinity means, is just keep going. You'll always keep going up. And if you terminate after a finite number of terms, you're just going to add up and get some number. And it's always going to be a finite number. It may be large, but it's going to be finite. Correspondingly, here, when you're adding up infinite number of terms, it's not so clear whether it will be finite or whether you'll go off to infinity and get infinitely larger, or whether you'll just kind of alternate between two values. The formal definition of continuity is this, or formal definition of convergence is this here. So we say this series converges to a given limit, let's say L, if and only if this is true. Basically, you can be guaranteed that after a certain point, if you add up not the whole series, but just a part of it, if this ending index value is large enough and it is large enough past this given n value, it'll always be really close to the L. It'll be epsilon close. So the idea is you pick a small L, you guarantee or try to guarantee that you can find a capital N big enough such that as long as your ending index is larger than that, you're going to be really close to epsilon. And then you take a smaller epsilon, you kind of squeeze these two together in some sense. So formally, if you can do this, no matter what the epsilon is, if you can find this value such that this is true, then we say that the series converges to a real number, to some L. Otherwise, it diverges if it doesn't do this. Now let's look at some examples because this may be a little abstract at the moment. If we look at, let's say, the series 1 plus, say 1 plus 1, and so on, which we could write as just the series where we add up 1 infinitely many times. This is a divergent series. The reason it's divergent is that we can guarantee that the sum is going to be as large as we possibly want. So if you think the sum is equal to 1,000,000, you can just add up 1,000,001 terms, the first 1,000,001 terms, and you'll get something larger than 1,000,000. So that means, well, it can't be 1,000,000. If you think it's 1,000,000,000, you can add up the first 1,000,001 terms and get something larger than 1,000,000,000. So it can add up to 1,000,000,000. And this is true for any finite number you pick. No matter what, you can get this sum to be larger than any single finite number. Therefore, it can't be any finite number. That shows that it's divergent. The same is true for this series. If you have, let's say, 1 over n, and n starts at 1, this looks like 1 plus 1/2 plus 1/3, and so on. This is also divergent. It's not as clear, but it does have the same effect as this first one. You can show that by adding up enough terms, you can get this sum or a partial sum to be as large as you want. It ends up being something like if you take the partial sum, let's say P1, that's just 1. The partial sum P2, that's 1 plus 1/2, which is 3/2, of course. The fourth partial sum, which is 1 plus 1/2 plus 1/3 plus 1/4, is going to be greater than 4/2. You can show this is equal to 2/2. The eighth partial sum is going to be greater than 5/2, and so on and so forth. The 16th partial sum of the first 16 terms, is greater than 6/2, and you can keep going here. You have to jump out farther and farther for your ending index value, but it doesn't matter. You have an infinite number of values. You can jump out as far as you need to. And the point is you can jump out far enough with your index such that you can get it to be as large as you want. So that's a brief argument or outline of the argument showing that this is divergent. On the other hand, if you make a slight adjustment, you may remember, and actually let me put this over here, out of the way. On the other hand, you have the series like so, 1 over, let's say, 2 to the n, kind of your classic convergent series. That looks like this. This is convergent. And it converges, let me say it like this. This converges to 2. And you can essentially show that if you pick an epsilon to be any small value, then you can go far enough out with your terms such that the difference between that partial sum and the value 2 is smaller than epsilon. It's as small as you want. So you can squeeze this thing to be as close to 2 as you would like just by taking more and more terms. That's the rough idea. That's not a formal proof I've written, but that gives you the idea of how you would prove it. And now I'm curious. So here's a question for you. Do you think, yes or no, and right or wrong, I don't really care at this point. I'm just getting a sense of where you're at. Do you think that this is convergent or not? And why or why not? It'll maybe also give me a sense of what you remember. Actually, that should be, let's say, n. Let me just make this adjustment. So this looks like what? 1 minus 1/2 plus a third minus a fourth, and so on. So what do you think? Convergent or not with this last series based on what you remember? And if you think it is convergent, why? If you think it's divergent, why? Okay. Thank you guys for those of you who put something in chat. I see some good comments. Someone pointed out the following fact. You're going to have a jumping back and forth criteria. Let's see if we can graph this decently. First, you'll have 1. So let's just say we have the first 1 there. If you were to plot that, say here's 1, the value of 1, and that will happen when n is equal to 1. If you just have the first term, let's call this, I guess, the n-axis, and this will be p of n, the first n terms. The first one, if you just have 1 term, it's going to be 1. Now, if you take 2 of them, 1 minus 1/2, that will, of course, give you 1/2. So say we plot the point here, and this is 1/2. This is 2. So we get the first 2 terms. That would be like p of 2. And just to be clear, this is p of 1. Do the same thing. Maybe now we use green. We take the first 3, which is p of 3. And let's see, we're going to take, I think that's going to be what, 5, 6? We're going to take 1/2 plus 1/3. 3 plus 2 over 6 is 5/6. So we get something like this. And now I don't think it's maybe too hard to recognize that we're going to, like I said, oscillate or jump back and forth. And what's going to happen is if you kind of connect these dots, you get this, this, and then you'll go down a little bit and then up a little bit and so on. It'll kind of look something like that. It's actually for this reason that it does converge. And in fact, this is not a formal proof, but it kind of gives the idea of why you might think it does converge. Because your envelope gets kind of smaller and smaller, the envelope of values it could be, And this envelope keeps shrinking if you look closer and closer or take farther, larger values of n. You look farther out. So because this envelope is getting smaller and smaller and smaller in the right way, you actually get that it converges. And that's by something called the alternating series test. So this converges by the alternating series test. Now, I didn't necessarily expect you to remember that test. I was just kind of curious if people did. It looks like a few did, but most didn't mention that, which is totally okay. It's just the point to see where you're at. Now, this does lead us to the notion of convergence tests. And you may remember from Calc 3, even if you don't remember the specifics, but just that there were a lot of them. And let's kind of review what they are. All right. The two biggest ones are, without a doubt, the divergence test and the ratio test, at least for us at this moment. The others can be very important, especially in maybe different areas. Some may use comparison, limit comparison, integral tests more, just depending on what type of models and situation you're working with. But for what we'll do, especially since we're working with power series, besides the divergence test, which is maybe you could call it the divergence check because it's just a really quick check to see if it's divergent or not, or see if you can claim it's divergent right away. Otherwise, the ratio test will be something that you use with power series quite a bit. Namely, there, what we'll do is we'll use that to find the radius of convergence. That'll be the primary purpose of the ratio test, at least later. And you wouldn't do that with just a normal series. You would do that with a power series. And the difference, just so that terminology is maybe not too alien, there's a series like this where you're just adding up a bunch of constants. So this we would just call a series, or I'll use just the phrase series. But then a power series looks like this, where you have a variable x and you're taking increasing powers of that variable. So the power part comes from this here. Okay, so let's remind ourselves what's up with the divergence test and then look at the ratio test, since that'll be the big one. Say we had the following. The series, say n factorial over 2 to the n, and maybe that's it, where n is going to be 1 up to infinity. The question is this something we can say is divergent by the divergence test? Now, what the divergence test says is look at the terms, decide, do they go to 0 or not? If they don't go to 0, if they don't decrease, then you can guarantee that it's divergent. If they do go to 0, it doesn't guarantee it is convergent, because the harmonic series is a counterexample. If you take the series like we had before, 1 over n, the terms go to 0, but you have that it's a divergent series. So the terms going to 0 is not enough. However, it is a condition that's necessary. So we say it's a necessary but not sufficient condition. You need to have this at least. So if you don't have it, since it is a necessary condition, you're going to get that it diverges. So if you don't have terms going to 0, you will definitely diverge. If they do go to zero, you don't necessarily converge. So that's why it's the divergence check. You check it, and maybe it tells you it's divergent. Otherwise, you have to investigate more. The question, and maybe you can say in chat just to get a sense of, I don't know, where you're at with this. What do you think? Do you think that the terms here go to zero or don't? Do you think that they don't go to zero? And if so, that would mean by the divergence test that it's divergent. So you can just say in chat whether you think the terms go to zero or not, or whether you think it's convergent, divergent, just whatever your thoughts are. Okay, you guys are putting some good things in chat, which I appreciate. Let me erase this for the moment. Okay, lots of good comments, and I appreciate those. Let's investigate, and you may change your mind as we look at this, but let's see. If we just look at the first few, and by few, I'm not sure how many exactly, but I think the pattern will reveal itself at some point. If we take n is equal to 1, I think that's 1 factorial over 2 to the n, or 2 to the 1, which is, I'm going to write it like this, 1 over 2. Then n is equal to 2. We now have 1 times 2, and then 2 times 2. N is equal to 3. We have 1 times 2, because that'll be 3 factorial up top. And then we have 2 times 2 times 2. N is equal to 4. 1 times 2 times 3 times 4. 2, 2, 2, and 2. And I think by n is equal to 5, it should be clear what's happening. And let me space these so it's as easy as possible to see. All right, if we look at this, what we see is that, let's say n is equal to 3. It's the same thing as n is equal to 2, with the exception that you're multiplying by 3 halves. These are out of control. There we go. And then likewise, with n is equal to 4, it's the same thing as n is equal to 3, but multiplied by 4 halves. And this pattern continues. So we essentially take what will be 1/2 and we multiply it by 1 and we get 1/2. Then we take 1/2 multiplied by 1, which is 1/2, and then we multiply it by 3 halves. Then take that value, multiply it by 4 halves, or 2. Take whatever value we get there, we multiply that by 5 halves, and so on. What we end up getting is 1/2 times 1 times 3 halves times 4 halves times 5 halves, and so on. Since each of these are larger than 1, and you're taking this positive number and you're multiplying it by something bigger than 1, it increases. Then multiply it by 4 halves bigger than 1, it increases and increases, and so on. So the terms, they actually just get bigger, so they certainly don't go to 0. So by the divergence test, this is a divergent sequence, or a divergent series. Okay, good. Now let us look at another one. Let's look at this one. We have, maybe I'll just write it expanded like this. Say we have 1 plus -1 plus 1 plus -1, and this pattern just continues. So what do you think? You can just say in chat either way, only I'm going to see it. And I don't mind if you're right or wrong. I just want to know what you think. What do you think about this series, is this convergent or divergent? Okay, thank you for those of you who have put something in chat or are putting something in chat now, and feel free even as I'm talking to add something. This is actually a series I love because it's very neat. You can look at it in different ways and get different results. So here's what I mean by that. I'm just going to take away the parentheses so we get one, let's say -1, +1, -1, +1, so on. Now, if I take away the parentheses around the -1 and I instead put them around here, what we'll see is that if you add all this up, what you'll get, of course, is 0. If you group all the pairs, 1 and -1, you get 0. Okay, so it seems like the series is equal to 0. But, and here's why I like this so much. It's, in my opinion, very neat. You can alternatively group it differently. So if instead of going 1 minus 1, I group it like this, where I group these two together, and then these two together, and so on, what that would look like is 1 plus, and now I'll put orange parentheses to kind of emphasize the different grouping. We have -1 plus 1. Then we have plus again, -1 plus 1, or plus 1, plus, and finally -1 plus 1. But then that would keep going. If we group it like this, what you'll get is actually 1. Now it's the same numbers, note that we have this 1 is always in the same place, this -1 is always in the same place, and so on. All that's different is that we've grouped them differently. We've put parentheses in different places. So it seems like, well, they should be the same if you just move the parentheses, but in fact, no, that's not true. They're very different. Moreover, you could even group this in creative ways so that what you get is any integer. You could have any integer you want here just by grouping appropriately, because what you can do is you can sort of rearrange and get, a bunch of ones to begin with. Let's say you've got alpha ones. And then after that, you can group it so that you have -1 plus 1. The reason you can do this is because infinity is very weird. And you always have an infinite pool of things to pull from. And just depending on the order in which you pull from that infinite pool, you can add up to really any number, any integer you like. Any, I should say. Actually, even any negative integer. You could alternatively do beta, where you have a bunch of -1s, and then group them in the same way. And again, this only works because infinity is weird like that. So maybe you have beta number of -1s, or absolute value beta maybe. Now this is kind of maybe the more theory than we need at this point, but I think it's very interesting that you can add up the values in different ways to get different numbers. You have the same number of ones, quote unquote, in each case, but you get different values. Now that should hopefully be a little bit convincing as to why this diverges. Because if you thought it added up to a certain number, you could just find another number to add it up to that's way different in value. Alternatively, actually by the divergence test, if we look at the values individually, the values do not go to 0. We just alternate between 1 and -1. So by the divergence test again, it's divergent because the terms don't go to 0. They just alternate 1, -1. Yeah, so lots of fun, weird things can happen with series and infinity in general. Infinity is pretty cool. Now let's look at this next one, which may or may not be tricky. Say we had, let's see, let's do this one. Oh man, I can draw the symbol, I swear. Suppose we had 1 over 3 to the n, where n is equal to 0. Okay. What do you guys think about this one? Convergent, divergent, why not? What are your thoughts? And again, only I'm going to see it and I'm not judging. I'm just curious what you think. Okay, as usual, thank you to those who are putting something in chat. These are very interesting comments. I appreciate them. Okay, let's take a look. First, do we agree that if you look at the terms individually and then kind of jump from to increasing n values, that the terms themselves will go to 0? We have 1, and then we have 1/3, and then we have 1/9, and so on. It seems that these will go to 0. We can get this to be smaller and smaller and smaller if you just look at the terms. So on the basis of just looking at what the terms do as, let's say, a sequence, that will go to 0. This goes to 0 as n increases to infinity. The question is, since we now don't have it, since it does go to 0, the divergence test won't apply, because the divergence test says if they don't go to 0, then you know it diverges. What the divergence test doesn't say is what happens if they do go to 0. And that's an important part. So divergence test, an important point. Divergence test says that the first part of the statement is if the terms go to 0, then what follows is that the series diverges. Now, I can't stress this enough. What the divergence test does not say is what happens if they, if the terms don't go to 0. So what the divergence test does not say is what happens if they do go to 0. It says if you have to start with, the terms go to 0, you get that the series diverges. But if they do go to 0, divergence test doesn't really say. So there's two cases. They go to 0, they don't. And if terms do go to 0, divergence test basically says, I don't know. Don't ask me. So it's only useful in the case where the terms don't go to 0. It's really important to note the divergence test does not tell us anything about what happens when they do go to 0. It's a really, really easy thing to get mixed up. And I see a few people were maybe thinking because the terms do go to 0 that it does converge, but not necessarily. And again, let me point out the most classic case of this, which is what's called the harmonic series. If you look at the series 1 over n, where n starts at 1 and goes to infinity, this diverges, and yet the terms are going to 0. So just consider that. All right, with that said, this series, however, will converge, not by the divergence test, but because it's a special type of series called the geometric series. So this converges, and it converges since it is a geometric series. And it's a geometric series with, let's maybe use the notation R is equal to 1/3. In very rare cases are we able to actually decide what the series adds up to. Geometric series is one of the few cases where we can do that. And if I remember right, it's going to be 1 over 1 minus 1/3, which is 1 divided by 2/3, which is indeed 3/2. But that's, again, a very special case. Geometric series are one of the nicer series because it's really easy to decide whether the series converges or not. Namely, this R value has to have absolute value strictly less than 1. And they're further nice, not only because you can tell easily whether they converge or diverge, but you can also tell if they converge exactly what they converge to. That's very rare. All right, let's do maybe one more. And this might be a little bit harder, maybe not, but let's see. Let's say we're adding up 3 to the n times n divided by n plus 1. And we're taking n to be 1 out to infinity. And actually, let's do 4 times 4 to the n plus 3. Okay, I'm just going to clean this up, but it's going to be the same series as what I've got here. So what do you guys think? Is this convergent, divergent? What are your thoughts? And if you're not sure, you can even just say, well, I think it converges just because that's, what my gut is saying. Going with your gut is a valid thing to do in math to start with, because you got to start someplace. And once you have basically a hypothesis, I think it converges, then you can sort of test it, and just gives you a place to start out. Okay, let's take a look at it. Now, there's a few things you could use here. You could use a comparison test. You could compare it to, I think, geometric series. And there's kind of an art to comparison, because with comparison test, you're really just trying to show that it's either the terms are greater than some divergent series terms, or they're less than some convergent series terms. And you kind of have a lot of flexibility in trying to do that comparison. Otherwise, whenever you have a case of, let's say, ratios of like n over n plus 1, like we have here, or different values to a power, like 3 to the n, 4 to the n plus 3. When you see things like this, ratios of integers or ratios of powers, like 3 to the n, 4 to the n plus 3, in those cases, using the ratio test will often get you what you want. So let's try using that here. What the ratio test says is that we should look at a ratio and see whether the limit of that ratio is 1 or is less than 1, is greater than 1. And if it is 1, then we have to say more. But we're essentially comparing it to 1. But it's the ratio as n goes to infinity. So we take the limit as n goes to infinity of this thing, except we do n plus 1. So actually, let me really make it look like a ratio. So we have this. We're going to then divide it by the same thing, but in the top, we're going to change all the n's. I'll just run through the algebra really quick. I think the algebra is going to be something to the effect of n plus 1 squared over n times n plus 2. Then we're going to have 3 divided by 4. The limit of that, we can pull out 3/4, because 3/4 does not have anything to do with n. We get n plus 1 squared over n times n plus 2. I claim that that limit is going to be equal to 1 because it's n squared up top, n squared on the bottom, largest terms. This is 3/4. That's less than 1. If it's less than 1, this limit of the ratio, then we have that it converges. So this is a convergent sequence. Converges by the ratio test.
To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.